Hi, my name is Calvin Woolert, and in the last video I introduced the concept of continuous energy optimization. In this video I'm going to show you some real-world aspects of continuous energy optimization in practice. So one example we'll look at is a sample chiller plant. In this plant, as in many plants, chiller logs are routinely taken, but the data is not utilized. It's simply written on a clipboard that's hanging by the chiller. And also, in many plants, the assumption is made that the chiller's running, the building is cool, everything's fine. That could be a chiller, it could be any other piece of equipment. By taking those logs that are already being collected and entering them into a computerized system, every data point can be analyzed and problems can be spotted early. The point here being is that you don't have to have a utility monitoring system that actually meters all these points. If you're already collecting this information, you can simply plug it into the system and then run diagnostics on that data in your utility monitoring system. You can see things like fouled condenser or evaporator tubes, partial loss of refrigerant charge, cooling tower problems, or water flow problems. Non-condensables in the chiller, which I mentioned earlier in the previous video, incorrect chilled water temperature, condenser water temperature set points. Are the chillers operating at poor part load conditions or operating when unnecessary? So in this example, you can say, okay, using continuous improvement program, by taking the data that's already being collected, it may alert to the fact that, hey, I have a high approach on my evaporator. Approach being the difference between the refrigerant temperature in the heat exchanger and the leaving water temperature from that heat exchanger. If the difference in that temperature or that approach starts to increase, that means my heat exchanger is not working well. And so when that happens, you can be directed into an automatic system which will tell the operator what to check. First thing to check is, are my instruments reading correctly? Are the measurements correct? And then you can go and review the maintenance logs and determine, did I add too much oil, or is there other problems such as scale in the evaporator, tube bundle on the water side? There's lots of different things. So the point is that problem can be spotted early in a chiller that appears to be operating okay using the data that you already have. So as an example, a chiller that's, quote, running fine could be using as much as, or lose as much as 30% efficiency. In our previous webinar series on financial indicators, we did a life cycle cost analysis of a 600-ton chiller. And in using that particular analysis, if a 600-ton chiller was operating with a 15% efficiency loss, that would cost $29,130 a year. But if it's losing that much money each year, I would argue that it's not working fine. Here's another example. This is an actual air handling unit located in the Green Bay, Wisconsin area. And we put in some data logging to be able to track the delta T across the heating coil of this air handler. We also monitored the outdoor air temperature. We monitored the mixed air temperature, which is a combination of the return air and the outdoor air, as well as calculated the percent outside air that was being introduced at any given time. If you look at this data, it doesn't really tell you a whole lot. However, to the trained eye or to a program that can actually look at these variables and compare them and draw conclusions, we see that there's a lot going on with this air handler. There's a lot of things that aren't working well. For example, the mixed air temperature is floating around and not being controlled well. It's very clear that the economizer is not functioning properly. The minimum outside air being delivered to this space is about 50% on average when the economizer is not working, when it's not enabled, I should say, when it's not supposed to be working, which means the space is being way overventilated, which is a huge energy impact, particularly in a climate like Green Bay, Wisconsin, where it's quite cold. The unit is running at night when this area is not occupied at night, so there's no point in having it running. Plus, the heating valve appears to be stuck on because we're getting a constant delta T across the coil even when it's trying to cool. So you got simultaneous heating and cooling. This air handler is probably using 60 to 70% more energy than it would if it was properly functioning. However, according to the building operator, the unit's running fine. The space is cool, not a lot of complaints. Temperatures are being met. So this is a real-world example of how continuous diagnostics can provide energy savings and also help you manage your program. And the beauty of these things is they don't require significant capital investment. They're basically programming changes, set point changes, maintenance avoidance. If you look back at the chiller example, having a fouled evaporator tube could eventually lead to unscheduled downtime, which could be incredibly expensive. And that's an added side benefit of having a program like this. If you want more information, please continue to see our other videos, or by all means, please contact us. Thank you.